So we can start today's session by Professor Hari Krishnan. Professor Hari Krishnan is a faculty from the Cochin University of Science and Technology from the Division of Mechanical Engineering. You were all introduced to him yesterday, and yesterday we had an excellent session by him. And today also we are looking forward to a very good session by Professor Hari Krishnan, and his talk will be carried forward by Mr. John Pinto, who will be handling the demonstration part. So Professor Hari Krishnan will be talking about the logic of meshing in 3D today in the first half. And then Mr. John Pinto will take the hands-on session. So over to you, sir.
So yesterday, I hope all of you enjoyed the tutorial session also, in which tutorial I think you did a two-dimensional meshing, a two-dimensional body meshing using blockMesh utility. So we will actually go further how to go ahead with a three-dimensional body or three-dimensional domain, and what are the things we should actually keep in mind, especially when we use blockMesh. So as I said, so this is only using blockMesh utility. As I said yesterday, it is also possible to make mesh geometry, etc., using some other softwares or other utilities like SnappyX Mesh or even ANSYS, ICM or HyperMesh or any other meshing softwares. So here I will be focusing more on blockMesh utility. Okay. So the contents are what I thought was I will just give the brief overview about the process, especially let's say three-dimensional pipe case, and followed by the tutorial session by John. So the basic background I will be explaining, and then you will be having a hands-on session. You will be also replicating the meshing, 3D meshing of the 3D pipe with the help of John by following the spoken tutorials, right? So we will start with, yesterday we stopped at a simple rectangular block mesh, right? Lid-driven cavity problem or a two-dimensional channel flow. So basically we have a two-dimensional domain. Okay. So now we will go ahead with exploring the other options available in the block mesh, especially how do we make non-uniform mesh. Yesterday I discussed it's also possible to make non-uniform mesh in this block mesh, and how do we make curved geometries, and some tutorials is already available tutorial, plate fault tutorial, especially not tutorial in the sense the block mesh file. We will just see how they made the block mesh corresponding to the plate hole tutorial, and finally we'll see what exactly is a 3D pipe, how do we model 3D pipe, etc. Okay, so to begin with, let me summarize what we discussed yesterday. So we discussed about the blockMesh command in detail, and blockMesh command, whenever we type blockMesh in the terminal, so immediately it will call blockMesh dict file present in the system folder, and in what are the instructions given in the blockMesh dict file will be used for generating the mesh. And this is a typical example for a, let's say for a cavity problem. I just copy pasted the snapshots from the blockMesh dict file. So what we essentially do, these are the commands, basic commands. Some of them we already discussed. Convert to meters. So we know that when we make a geometry, first thing is we should have points. So we need to define the vertices first. So that is what you can see here. It is followed by block. So we are connecting these vertices to make a hexagonal block, and that is what we mentioned here, blocks, hexagonal, then followed by the vertices, followed by the number of divisions in the x direction, number of divisions in the y direction, and number of divisions in the z direction, followed by something called symbol grading. So that we didn't discuss yesterday, so we will discuss that part in detail in the upcoming slides. And what is symbol grading, how do we give non-uniform mesh, how do we generate non-uniform mesh, etc., with the help of symbol grading. And this will be followed by edges also we didn't discuss yesterday, and we will be also discussing about, we also discussed about boundaries, how do we define top walls, and what is a pattern, or how do we identify these vertices, etc., top wall, bottom wall, or fixed walls, front and back walls, etc. Okay, so when we execute blockMesh command, you will see we will be having mesh will be generated, and we will be able to see that with the help of Paraview software. So what is non-uniform grading, or what is non-uniform mesh? So as you can see from the right hand side figure, so the meshes or the cells very near to the left hand side wall, that is here, you can clearly say that the cell size is very small or very fine, and slowly there is an increase in the cell size value when we travel from left side to right side. So typically when we have wall driven flows or wall driven flows, so we generally prefer non-uniform mesh or very fine mesh near the walls in order to capture each and every eddies, in order to capture the flow physics in a proper way. So the main advantages are we can reduce the total number of cells. So instead of keeping the cell size as the smallest one throughout the domain, so what we do, we will keep the fine mesh wherever we have steeper gradients. Then we will keep the coarse meshes where there is no steeper gradients. Okay, so that basically help us to help us to reduce the computational time required for the simulations. So how can we achieve these kind of measures using a blockMesh utility? So before that, we should know there is a term called expansion ratio. So the symbol grading command is used for generating non-uniform mesh, and the expansion ratio is defined as, so there is, let's say you are going to connect, you can just see this figure, you're going to connect two vertices by using an edge, let's say 0 to 1. And we know that when we keep the number of divisions in x direction, let's say 10, so that will initially, that will divide this line equally, let's say into 10 sections, right? So when I give symbol grading with certain values other than 1, what happens is these are known as the value present within this bracket is known as expansion ratio. Expansion ratio is defined as the, I am moving from left to right, right? Okay, expansion ratio is defined as the cell width at the last, that is near the point 1, divided by cell width at the first cell. So the ratio between the cell width of the last cell, that is at the end point, near the end point, that is near the point 1, to that of the cell very near to the starting point. So this direction is also very important. So you can see when I keep expansion ratio greater than 1, okay, what happens? The final one will be much higher as compared to the initial one. So obviously gradients are, or fine mesh is near to this edges. And what if I keep this instead of 10, if I keep 0.1, so higher, the bigger cells are near this point, near this 0.0, and smaller cells are near this 0.1. So in this way, we will be able to fine tune if you want refinement in this particular near this wall, it is possible by keeping it greater than 1 as a expansion ratio. Expansion ratio, it's up to you to decide how to proceed, etc. Generally, if it is greater than 1, we will be having coarse mesh when we move towards positive x direction and vice versa. So as I said, expansion ratio is the ratio of the width of the end cells along one edge of a block to the width of the start cell along that edge. So this is what happens when I change it slightly. So same case, I just kept 0.1 instead of 10 earlier cases. So previous case here you can see instead of 10, what I did 1 by 10, I just kept 0.1. That is, the first cell height is very high, 10 times higher than that of the last cell height. Okay, so this is an example for non-uniform grading in a simple application using blockMesh. So what happens when we need a refinement in both sides? So what we need to do, we should consider two blocks, and generally we should consider two blocks and keep grading one in the positive, let's say greater than 1, and the other one is less than 1, such a way that we will have a fine mesh near the, let's say, left hand side wall as well as right hand side wall. Okay, that is one of the utility, one of the additional thing available in blockMesh utility. And now we will see geometry with curved edges. So it is not, so yesterday we were discussing about very standard geometry, that is rectangular block. In most of the cases, we may have some curved geometries also. So in that scenario, is it possible for us to identify, or is it possible for us to make a curved geometry in blockMesh? Yes. So in order to do that, what we need to do is we will be using an option called edges. So after vertices and after blocks, there is an option called edges. And yesterday we saw that was empty. And we can see this is an example in which same lid-driven cavity problem. I made a curve here in this particular end. In this particular end, in the sense between 2 to 1 as well as 6 to 5, or 1 to 2 and 5 to 6, I made a curve. So how is it possible? So let's say this is point number 1 and this is point number 2. So we know that if you want to make a curve, let's say I'm going to connect these two with an arc. So the command I used here is known as arc, followed by the vertices 1 and 2. So 1 and 2 followed by a coordinate. So basically this coordinate indicates any point within the arc. So for time being, I just kept this as a midpoint. So let's say this is 1.2, 0.5 and 1. So what was the dimensions, coordinates here? I think this was 1, 0 and 0, and this was 1, 1, 0. So this is the third point. So when I say arc 1, 2 be followed by a coordinate, so it will automatically make a edge that is actually arc that is going through this particular point. So if you want a different arc, you can keep different coordinates such a way that we may have different arc. So when we modify the existing lid-driven cavity problem or a 2D plane channel flow, what we need to do is we should also make, let's say I want to make some mesh something like this, then we should also make two edges, especially 1 to 2 as well as 5 to 6 or 6 to 5, both curve. Then we can do the same thing whatever we did earlier, like hexagonal number of divisions. If you want refinement, then it is also possible, right? So this is just an example for making a curved edge using blockMesh utility. Okay, so as of now we were discussing only about a single block in general, right? So I had only single block. So let me ask you one question. So in the next slide I have two figures, mesh 1 and mesh 2. Okay, so can you just tell me what are the major difference? You can just type in chat box what is the major difference from mesh 1 and mesh 2. Oh, which one is good according to you? Okay, someone said mesh 2, O grid. Vertices I didn't showed here. Yes. So most of you agree that second one is better compared to the first one. As you can see here, you can see there are some cells in which, so as I said, we have uniform mesh, that is structured mesh as well as unstructured mesh. And there are something called mesh quality we were discussing, like skewness of the cell and aspect ratio of the cells, etc. So there is a preferred range of aspect ratio, skewness values, etc. And if you have a very highly skewed cell, what happens? Either it may leads to some error or it will take long time to get the results. So we prefer our meshes or cells in a range of skewness values, range of aspect ratio values, etc. So we try to avoid highly skewed cells when we make meshes. So you can see there are some cells in which you can see here some skewed cells are there. So here you can see in this cell I don't have actually a 4 edges. I have only mainly 3 edges, especially in these corners. So the first one, what I did is I generated the geometry by using the same coordinate from the lid-driven cavity problem. Then instead of a rectangular straight line, I was trying to connect it with the help of arc. So when we have a 4 arc with a proper radius, what happens? It will make a circle. Then same block mesh, whatever we did, I used, and the mesh what you can see here is obtained by using the same methodology what we were discussing earlier, right? On the other hand, I did a different method. I used multiple blocks to generate mesh as shown here. So interestingly, you can see we have a rectangular block here which is having equal number of divisions in the x direction, maybe not equal. We have divisions in the x direction as well as y direction, and you can see there are some radial lines. This was not present earlier. You can see these radial lines are not there. You can see the radial lines like a spider net. You can see then we are dividing this radial net in the radial direction, right? So in theta direction as well as r direction, we have number of divisions. So in order to make these types of meshes are known as O-grids. Typically for circular geometry, we always prefer O-grid or similar to O-grid approaches. And if you want to make these kind of grids, what we need to do is we should actually consider multiple blocks. As an example, you can see I consider for a circular body, whole circular body, let's say some complete circle, I will make multiple blocks in which in the center I have a simple rectangular block, okay, and on followed by, you can see there are some rectangular, it's not rectangular block, we can say we have 4 sides and we have 1, 2, 3 and 4. 4 different blocks are surrounded by this central rectangular block, and this edges, what we will do, we will keep these edges as an R, right? So these edges as a R, these edges are as a R. Then what we do, we will give the, so we have 1, 2, 3, 4, 5 blocks, and each side edge we will divide. So let's say I need to give the number of division in this direction. So automatically here also it will come. Then in this direction, then in this direction also. Only 3 directions. So x direction, y direction, and radial lines. So these edges also we need to give the number of divisions such a way that we will get very clean mesh, like as I showed earlier. So what if you have a semicircular geometry? So we'll just divide this. So still we have, so this is a central one. Then let's say 2, 3, 4. 4 blocks will be there compared to 5 blocks. So if it is 1/4 of the circle, then same methodology we will be adopting. So essentially we need to generate multiple blocks, and basically when we have multiple blocks, we will also have a better control also. And the last one is known as L grid. So when we have 1/4 one. So the right hand side figure, the mesh final one, you can see here is taken from a tutorial called plate hole tutorial, which is already available in open form. So you can see it's a combination of a 1/4 of the circle followed by a rectangular block. So the blocks you are going to see here is, so here we have a semicircle, 1/4 of the circle, and hollow circle, you can say, right? It's not even complete circle. So I have a circle like this, then I have a rectangular block like this here. And here I have one of the edges as curve, and other 3 edges are essentially straight line, connected with straight lines. So when we have a geometry like this, then we should know how to decompose these blocks. So that is one of the main challenges, and you may need to identify the coordinates, and then we will do blockMesh utility. So this is typical example for a circular cylinder. You can see in Z direction, let's say this is X direction, Y direction, and Z direction. The top one may looks like this. So we have a rectangular block here, and then we will have a radial divisions as we saw earlier. Okay. So now I'm just going to explain the basic idea as we discussed, that is plate with the hole. So this tutorial is already available in open form, and the details regarding the blockMesh file is clearly explained in the user guide also. I will just share the location of the tutorials in the chat box. You can later on also. So this particular tutorial, so there are hundreds of tutorials. So many tutorials are available within the open form. Then you can also explore other not only related to fluid mechanics and heat transfer. You can also explore the tutorials in the other solver directories also. For example, this is an example I took from a stress analysis solid displacement form solver. So this tutorial you will find in tutorial folder, then stress analysis, then solid displacement form, and the tutorial name is known as plate hole. So what we essentially in this problem, what we are going to do is we have a rectangular block, we have a hole in the center. We are applying stress in the both direction, that is sigma value is 10 kPa in the both direction, and we use open form for solving this, that is for identifying the stresses within the domain. So because of the symmetric nature, they just consider only 1/4 of the domain. That will actually help us to save the computational time. So only 1/4 of the domain is indicated here as a shaded portion is considered. Then as I said earlier, I just divided these things into actually 5 blocks. So here you can see this part earlier I said it was 4. Here you can see this one also they divided into 2 pieces. So 0, 1, 2, 3, and 4. So 5 different blocks, right? Then here you can see this is an example, simply a rectangular block kind of thing. You can easily give the number of divisions in the X direction, Y direction, etc. Similarly for the other blocks also. So finally, this will be converted to this kind of mesh, right? So the details regarding the tutorials and the explanation regarding all these commands, meshes are already available in the user guide chapter 1, I think, tutorial. So plate hole, you can just search plate hole tutorial, and the details are available in the tutorial. Okay. So now the last one is known as 3D pipe. So I just started with simply rectangular block, that is a cavity tutorial, right? Then what I did, what we saw how to give a non-uniform mesh. Then the third case, we consider 2D case itself, but with a curved edges, like a lid-driven cavity problem with one of the side as concave or convex curve. Then we also considered multiple blocks. That is, when we have a complicated geometry, or if you want to make O-grid kind of thing, then we should consider multiple blocks in the domain. So now we are going to see the following the session, after my session, you will be doing a tutorial called a 3D pipe. So 3D pipe is essentially we are trying to simulate a case, that is laminar flow in a 3-dimensional pipe. So the dimension of the pipes are given like 0.3 meters in the length, and diameter is 1 centimeters. And as we know, we have certain boundary conditions, that is inlet, outlet, as well as wall. So at the end of the tutorial, you will be able to generate a mesh like this, right? So I will just see the basic idea behind 3D pipe. So as I said earlier, so we have a circular end here. So here the number of divisions is very straightforward because it's a straight line. If it is a curved pipe, then it will be slightly challenging. So here you can see it's a straight line. So the number of divisions along the flow direction is very easy. But when we have a circular end, you can see we should adopt O-grid kind of methodology. So how is it possible? So as I said earlier, we need to divide this domain into multiple blocks. So this is a schematic of the block shown here. So first thing is you should identify the coordinates. So let us see this case. Let's say the one of the end, let's say front face as well as back face. And back face view, you can see we'll start with the origin, which is indicated as 0, right? Then we need to identify points, like coordinates corresponding to these points 1, 2, 3, and 4. And the total diameter is given as 1 centimeters, right? And we should also identify the coordinates, that is 5, 6, 7, 8. Then we should also identify, if you are simply using edge without using edge command, it will connect that these vertices with a straight line. Then we should also know what are these coordinates, right? Then only we will be able to make the arc. So I am connecting 7 to 8 with an arc which is going to this coordinate. So I am connecting 5 to 8 or 8 to 5 by considering going through this coordinate. And similarly, wherever we have an arc, we should know the third point in which the arc goes through it. So this is for the back face. Similarly, we should also define the coordinates corresponding to the front face. So this is the center point, then followed by, let's say, 9, 10, 11, 12, 13, 14, 15, 16, etc. So then we have around 18 points. So 18 vertices are there, right? So starting from 0, 1, 2, 3 up to 17. So total 18 vertices are there. And the block structure is going to be like this. The central one, either so no need to keep this also circular. You can also keep the rectangular. You don't need to keep it arc. Okay. So the next slide, I will show you what happens if you keep this arc without arc. What are the major difference? Okay, so we are having basically 5 different blocks. Block 1, then block 2, 3, 4, and 5. And along the Z direction, you can see it will be extended. That is front face points. Let's say 10 will be connected with the point 2, and 9 will be connected with the point 1. Similarly, 11 will be connected with 3, and 12 will be connected with 4. Similarly, all these 4 points also 14, 6, 13, 5, 15, 7, 16, 8, etc. That's what it is shown here. So 10 is connected with 2, right? So 10 here and 2 here. Similarly, 9, 1, 12, 4, 11, and 3. So this is only for the block number 1. Okay, similarly, you should also know what are the points that is going to connect the block number 2 from the front face as well as back face, and block number 3, block number 4, and block number 5. So what happens when we connect these blocks? Then we need to give the number of divisions. So the number of divisions, so we are connecting, so example is, you can see here, we are connecting hexagonal block by connecting these many points, 1 2 3 1 2 3 4 9 10 11 12. You can just see 1 2 3 4 1 2 3 4 9 10 11 12. So the central block is indicated with this, and number of divisions in the x direction is given, y direction is given, z direction is given. Okay, with symbol grading. In this example, we just use symbol grading. Okay, so when we apply this, or when we have these things, let's say 18 coordinates, then connecting all those things, so each time we need to make a block. So earlier case, we saw that we have only one block. So here we will be having 5 blocks. So similar to this, in the block subdirectory, you will see hexagonal with 4 hexagons, right? Hexagonal with, this is first block, second block, third block, fourth block, and 5 blocks, sorry, 5 numbers. And we will be able to generate the mesh by using blockMesh command. So this is what happens, as I said earlier. So can you spot the difference between this mesh as well as this mesh? What might be the difference? What might be the reason for the variation? First one and second one, mesh 1 and mesh 2. You can just comment in chat box.
Hello.
Yes.
I think in mesh 1 there are some non-conformal elements,
Yes.
like the nodes which are not connected between the circular part in the center and the
yes.
other part.
Yes. The main thing is, you can see, as he said, Raghavendra said, these things are actually slightly skewed. Okay. The main difference was I connected these points also with the arc instead of a straight line. On the other hand, the interior nodes, like let's say 9, 10, 11, 12, here I just connected that with a simple straight line. So because of that, you can see here we have very good cells, and you can see here it is skewed cells. And so we generally prefer this. If I type check mesh command, as I said earlier, I'll be able to see that the aspect ratio is somewhere around, I think it's somewhere around 30, not 20. And on the other hand, I have 18. So lower aspect ratio is always preferred. And so that's what, when we make meshes, we should also know, even if we are using multiple blocks, etc., then we should actually check the quality of the mesh by typing check mesh command. And if we are having highly skewed cells, level high values of skewness, or when check mesh utility says the meshes are not okay, then we should open it in the paraview and see where are those issues. Then we should try to address that by using a different blocking strategy. Okay. So this is just an overview about making 3-dimensional pipe mesh. Okay. So the session followed by this will be hands-on session. Then you will have more idea. You will be also reproducing these things in your computer using the available files provided by FOSSEE team. So then I wanted to show you a few more things that is not part of blockMesh. So this was the thing mentioned in the, let's say for a 2-dimensional flow, we know that when we have a fully developed flow, we have a parabolic velocity profile. What do you think for a pipe flow? Is it a parabolic or some other shape? I will address your questions, whatever you mentioned in the chat box after this session. Okay. Is it parabolic, 2-dimensional, or 3-dimensional? What do you think?
2-dimensional.
Okay. For a 3D pipe?
Paraboloid.
Yeah, paraboloid. Okay. Yes, 3-dimensional. So is it possible to visualize that using paraform? What do you think? You understood? Okay, those who didn't understand, I will show you the next slide. So what happens is, so the velocity profile at any particular size is going to be in this way. So in 2D view, you may think it's like a parabola, but actually in a 3-dimensional structure, it may looks like this. So how to visualize that? I will just show you a small demo. That is, I already completed running the case. Let's say you can also try this after running the case. So the pipe case I completed, and I just opened it in the paraview, right? So then, so this is a typical contours. You can see pressure contours and velocity contours, etc. Now what I'm going to do is, I'm just going to make a slice at any particular location. So there is an option called slice in the left hand side, and I am going to make a slice in the Z direction, that is cross section of the pipe flow. Then if you just zoom it, you can see, if you see the velocity profiles, you can see at the central portion we have a relatively higher values of velocity, and it reduces towards the edges, right? So now I am going to use an option called warp. So basically it converts, you know that in these cells some values are filled, so it converts these values into a contour with the help of velocity vectors. So in order to visualize that, what I did, I am just going to make it reduce opacity of the outer domain. You can see that I reduce opacity and slightly increased. Then you go to warp and zoom it or color it with x velocity component or magnitude of the velocity component. You can see the three-dimensional structure of the velocity profile at that particular plane. Okay, so the utility I used, or the option I used, is known as warp. So basically it will help us to identify the three-dimensional velocity profiles in a channel flow. Okay, these are some of the examples on how to use paraview, etc. for visualizing the results. So let me go through. I also wanted to show you some other things which is not part of blockMesh, but it will be very useful, I felt. So exploring the other options available in OpenFOAM. For an example, there are a lot of options. As I said earlier, in the user guide, we have only 300 pages or 400 pages of material, and there are thousands of utilities available in OpenFOAM. And sometimes what happens is we don't even know these are the options available. For an example, let us say yesterday you were doing a case with a laminar flow, right? So I'm just going to open a tutorial called Pitch Daily. Okay, Pitch Daily is basically a channel flow with a modified, it's not a simple rectangular channel, slightly modified. Okay, in that I'm just going to explore. Okay, I will show you the other one itself, cavity. That will be better. So I will go to the blockMesh dial. I hope my screen is visible, right?
Yes, sir, it is visible.
Yes, thank you. So see, I am very curious to know what are the options available in edges. Okay, by default in cavity tutorial, there is nothing, it's empty. So what I am going to do is, I will just type some random name, let's say something which is irrelevant. Okay, it should be irrelevant. Okay, then I am just going to save. Then I am going back. Then I will run the blockMesh file. So what you can see here is, when I type this blockMesh, it will show that whatever I typed there is not valid. And the options available in that particular. So I just wrote something like trial. Okay. Then I'm just going to type blockMesh. So it will, you can see some error came. Okay. There are a lot of things. So these things may be a bit confusing, but if you scroll up, you can see, if you go to blockMesh sheds type, especially the file name. So they are saying in blockMesh dict file, I think this particular thing, valid blockage types are, so they are saying unknown blockage type trial, and these are the possible options. So either you should mention these options or you should not mention anything. So when I type some ROM commands there, what happened? They will say this is the option available. B-spline is there, arc is there, line is there, polyline is there, then project curve, splines, etc. So sometime what happens is, I used to keep this kind of method to identify what are the other options available. For example, yesterday you were doing an example with the laminar flow or RAS, right? RANS-based simulations, etc. If you wanted to know what are the options available other than RAS, you just type, instead of RAS, you just type something else and try to run it. When we run that, it will show this command not found. These are the options available. So with the help of this, you will be also able to identify what are the other options available. That is mainly because, as I said earlier, the documentation part is relatively weak. So once you get this keyword, then you will be also able to search based on this keyword. What do you mean by B-spline? You will get a lot of materials from internet as well as within the open form tutorials. Okay. Then another important thing is, let us say I saw that there is something called project, right? There is a option called project available. So I'm familiar with R, B-spline or line, polylines, etc. But I don't know what is project or where are the examples available within the open form directory with the name projects. So there is an option to search that also within that. That is this command. So within the open form tutorial, so when we copy paste this command, find form tutorials, name blockmesh dict, then grep-l, then projects. What they are doing is, in the open form tutorial folder, it will start searching all blockmesh dict files, and they will identify the keywords wherever they mentioned project. Then it will show the list of files, list of blockmesh files. I am just copy pasting this also in the chat box. I will show you. So you can see here, I'm just going to paste it. So what I can see is in compressible tutorials, compressible, in this particular tutorial also I used a term called project, and not it is available. So you can go through it and understand it. Or aerofoil or cooling sphere, these are the tutorials in which we used project term within the blockmesh file. And sometime we should also, along with this, sometime what happens is, we should know, we may not remember where we mention our fluid properties. Okay, so let's say new value, if you don't know where you kept new values within a file, that is, you are going to search within the file. So I can just type grep-r, then nu, then you can see within constant folder transport properties, nu is defined, right? So basically what I showed here is, I will be able to search within a document file, text file, with a keyword. If I type grep-r followed by the term, that term, wherever this term comes, I will be able to identify that. So the file directory name is shown here. Okay, so this is also very, very important. For an example, I will show you. I'm going to the tutorials folder available in the open form installation. So let us say I want to search within this. I want to know, there are some utility, let's say FOSSEE options widely used in certain cases, especially when we have a source term included in the governing equations. So if I want to find the tutorials in which we used FOSSEE option, so I can use this command. I'm just going to open the terminal in that particular folder. Then I will just type the grep command there. So grep-r, let's say FV option. So this is very case sensitive. So you should be very careful about the uppercase and small case. You can see in these tutorials, there is a utility, they use FU options. Okay, so these commands, I felt this is also very, very helping command, especially finding something within the text files, etc. Otherwise, you need to open each and every blockmesh file and identify whether any other options other than arc is used or not, right? So with the help of grep and as well as find command, you will be also able to identify these files, directories, etc. Then you can understand it, then you can start implementing it in your cases. Okay, so with this, I would like to end my session. I will just go through the questions in the chat box. 1 second. I will paste the grep command example here. So grep-r followed by the keyword what you want to search. So let me go through the questions. How can Akshay was asking, how can I make thermodynamic properties temperature dependent in open form? I'm not sure. By default, earlier it was not there. So recent developments, I'm not sure whether by default it is there. But there are some additional utilities. The main advantages of open form or open source software, as I said, it's a collaborative development. So there are some tools like SWAC for form and some other additional tool developed by some other groups it can be easily plugged into the open form, and we will be able to use UDF, that is user defined functions, let's say for giving inlet boundary conditions. So instead of a straight line, uniform velocity inlet, if you want a time dependent or a parabolic velocity inlet. So some utilities, additional utilities are also there nowadays. Even OpenFOAM also they started adopting, and it is also possible to do this kind of thing in OpenFOAM. So temperature dependent properties, right now I'm not sure. Some utilities might be there. Yes, it is already mentioned by Pranoy. We'll have to add T file in the zeroth folder and modify thermodynamic properties file in constant. Okay. Then yes, so Khodar was asking whether we need to give 0 and 17. It's not required because the origin in that particular example they just mentioned they started with origin. It's not required because this origin, especially the front face as well as the back face origin, we are not at all using for making the blocks. So I think it's not required. Yes, so there was another question, pipe flow problem. Isn't it more efficient to use axis symmetric simulations? See, if it is a laminar steady flow simulations, we know that it is symmetric, so it is fine. But if you are if you are just going to do with high velocity turbulent flow, etc., so always 3-dimensional domain will be better. So how to use blockMesh for inclined surfaces, chances of getting more smoothness flow over a triangular body? Yes, you should have a clear idea about how to make a block. There is something called blocking strategy. So there are some methods in which we can actually avoid inclined surfaces, especially highly skewed cells, etc. So different blocking strategies are there. So can we mesh an imported CAD file? So generally in blockMesh we give dimensions manually. Imported CAD files, I'm not sure. I didn't try till now. 3D pipe can create. Coach command is not from blockMesh, basically for decomposing the domain. So there are different methods available to decompose the domain for running parallel, right? So that part I think later stages they will explain. Yeah, it is possible to use tetrahedral elements also, no issues. So we can get blocking. So you may have to find some tutorials available online, especially some tutorials related to flow-past block bodies. We can also take this by taking domain like a rectangular box instead of. Yes, it is my. So Paridosh, I didn't get your question.
Yeah, this is Paritosh. Actually, I want to say why we have taken the coordinates of each point. Instead of, we can take a rectangular box, okay, that has all the pipe, and we can see x maximum, y minimum, and x like this coordinate, and we can put it in blockMesh.
Then it will be a rectangular domain only, right?
No, but it will contain my geometry has a circular pipe, and it will match it. Why I'm asking this question? Example, if you have a car, then how we are going to mesh it? It's not possible to take the coordinates, right, of a car.
Okay. Okay.
Then how
Yes.
we are going to mesh it if this is a car case?
So let's say you are keeping a car in a wind tunnel. Okay. It's like
Okay.
like that you are saying.
Yes.
Okay. Okay. Fine. So in those scenarios, we generally use snappy hex mesh.
Yeah.
So afternoon session, Chandan will be talking about external flows.
Okay.
So he will be able to give more details regarding that. He was working on flow past aerofoils and basically external flows. So he'll be able to answer your questions.
Okay,
Yeah.
got it. Thank you.
Yes, snappy hex mesh. We have used. I think it is possible, Raghavendra. In sender, I'm not able to see in your mesh what happens in the sender. If you don't use multiple blocks, then we may have a skewed cell there. So there are few people who raise their hand. Chaitanya, you want to ask something?
Yeah, hello, sir.
Yes.
So you mentioned like so while meshing, so you created multiple blocks, right?
Yes.
So on the outer surfaces, like I see a curved surfaces, but inside it is a tetrahedral kind of shape.
Yes.
So what is the governing equations that are getting used? Because it's either Cartesian or polar, or how is it solving? Because if I'm asking because I write codes from scratch. So we use either cylindrical system or the tetrahedral, like the Cartesian system. But this kind of mesh, so like because in Cartesian, like the neighbors are I+1, like J+1, something like that. But in this case, it is something different altogether. So how is the solver taking care of it?
So this is typically an example for a structured mesh. So
Yeah, exactly.
Yes,
Yeah,
yes.
yeah, right.
So it's Cartesian based, I think. I don't. Yes.
If it is Cartesian, but the cells are like curved,
Yes.
because then Cartesian won't apply, right? I think maybe in different blocks it is taking different like equations, or how is it doing?
The inner part of the blockMesh, I am not sure, because the people who developed blockMesh, they only mention how to use it and how to make modifications, etc. from the existing code. The basic logic, as you said, especially in the corner cells, they will have only 3 neighbors, right?
Right.
Yeah. So that part I'm not sure.
Okay. Yeah. Thank you, sir. Yeah.
Then group 11 raise their hand. blockMesh is a starting point, as Kodar was asking already. Gmesh and other softwares are there. It is already free. So blockMesh, those who are not at all familiar with especially CFD, those are very new to CFD and OpenFOAM. So we'll start with blockMesh because it's very simple and easy to understand. Once you start understanding blockMesh utility, then if you go with the Gmesh or any other packages, then they will be able to understand it better way. So blockMesh even in all workshops, we will give some sessions on blockMesh. How can we do machine jet propulsion? Complex geometry, it's always happy hex mesh which we use here. Okay. So if there are no doubts, then I will hand over to John. John, right? We will have a hands-on session.
Yes, sir. Yeah.
Okay.
Thank you.
Thank you so much, sir. Professor Harikrishnan, thanks a lot.
Yeah.